Today we are going to start a very important concept of solid state physics, particularly for the study of structure of crystals. So you can say that it is a very important concept of crystallography. Actually, the most of the properties of solids are anisotropic. It means the property of solids in different directions is different. Same property in different directions is different. So those properties of a solid depend on the direction within the crystal. So it becomes obvious that the specification of planes and directions in crystal must be known. And that's why it is a vital problem for the study of crystal structure or crystal analysis that we must specify the crystal planes and the different directions in crystals. So basically there are two problems. First one is to specify the direction of crystal plane, or you can say to specify the orientation of a crystal plane with respect to the crystallographic axis. And the second problem is how to decide how to determine the different directions in a crystal. For example, if you want to know what will be the direction of the normal to a crystal plane, how we can determine it? If your aim is to know what is the direction of an edge of a crystal plane, how we can determine it? So these are the most important problem, and the basic aim of these ideas is to discuss the different anisotropic properties of the crystal lattice. Okay. So this problem has two parts. In first part we will see the direction of the lattice planes. Actually, the direction of lattice planes are determined in terms of a set of three indices which are called Miller indices. Actually, Miller, was a British crystallographer, and he introduced a scheme to represent the orientation of planes in crystal. Okay, and so in his honor, these set of three integers or three numbers are called Miller indices. Okay, so in this lecture we will see the concept of Miller indices, how we can determine the Miller indices of a given crystal plane, and in the next part of this lecture we will see how to determine the different directions in a crystal. Okay, so I have mentioned it here. You can see that the scheme to represent the orientation of planes in a crystal was first introduced by Miller, a British crystallographer, and the indices of planes therefore are known as Miller indices. Actually, these Miller indices are actually the set of integers, and this is written in the symbol HKL inside this bracket, okay, without any comma. Actually, these indices are related to the orientation of the plane relative to the crystal axis of the unit cell, as I have told you. Okay, as you can see in this figure, I have shown here a crystal plane. Let us say it is plane ABC. The aim of, if this plane is denoted by the Miller indices HKL, then this HKL actually represents how this plane is oriented with respect to the crystallographic axis, that is OX, OY and OZ. But first of all, we will learn about how to determine the Miller indices of a given crystal plane. Actually, we will have to follow some steps which are very simple, very easier, and if you will learn step by step the method or the process of finding Miller indices, it will be very simple problem, and you can calculate the Miller indices for any given crystal plane. So let us see what are the different steps followed in determining the Miller indices of a crystal plane. In first step, first of all, we find the intercepts of the plane on the crystallographic axis in terms of the axial units or lattice constants ABC. It means if you see this figure, this plane ABC intersects the crystallographic axis at point A, at point B, and at point C. Now, what will be the distance of OA, OB, and OC? That is determined in terms of ABC. That is, we will take ABC, which are lattice constant, as units, and in terms of that we will represent only the integer. For example, if you say that on x-axis the intercept is equal to 2a, let us say, then in units of a it will be written only 2, not 2a. If the intercept of the plane, let us say, on the another crystallographic axis, that is y-axis, is, let us say, 3b, then you have to write only 3, not 3b. Okay, so in first step I have mentioned that the intercept of the plane on the crystallographic axis are determined in terms of the axial units or lattice constants ABC. Okay, now once you get the intercepts of the plane on the three crystallographic axes, then you have to take their reciprocals. For example, if the intercepts are 2, 3, and let us say 4, then you have to take their reciprocals. This is 1 by 2, 1 by 3, and 1 by 4. You have to take. As I have shown in this figure, that if the intercepts are h, k, l, then their reciprocals are 1 by h, 1 by k, and 1 by l. Okay. Now, after getting these reciprocals, in third step, you have to find the LCD. LCD means LCM of the denominators. So you have to find the LCM of 2, 3, 4. And you know the LCM of 2, 3, and 4 will be what? That will be simply equal to 6. Okay. So after taking the reciprocal of the intercepts, you have to find out the least common denominator, which is LCD. And LCD is what? This is simply the LCM of denominator. Okay. And once you get the LCD, you have to multiply all these numbers by that LCD. So in this case, you have to multiply 1 by 2 by 6, because 6 is the LCD, and that will be equal to 3. Then you have to multiply 1 by 3 by this 6, and that will be equal to 2. And after that, you will have to multiply this 1 by 4 by this 6. Sorry, this will be not 6 but 12. 2, 3, and 4. Actually, the LCD will be 12. I have mistaken here. So you have to multiply by 12, not by 6. Okay, 12. And then here there will be actually 6. Here will be 4, and here will be 3. Okay. So finding the LCD, we will have to multiply by that LCD to these reciprocals. And after multiplication, what you will get? You will get the Miller indices. We will actually simply write all those numbers inside the a bracket, as you can see in the form of HKL. Okay. So I have written here all these 4 steps. Now, taking a very simple example, illustrative example, you can see how these steps are followed. You can easily calculate. For example, I have taken that there is a crystal plane which cuts the crystallographic axis at 2A, 3B and 4C. It means the intercepts of this lattice plane on the three crystallographic axes are 2A, 3B and 6C. But in first step, you have seen we have to write these intercepts in terms of the axial units, or taking these A, B and C as units, you have to write the intercepts. So in axial units, we will write these intercepts only 2, 3, 6, not 2A, 3B and 6C. 2A, 3B and 6C are actual intercepts, but we have to find the Miller indices. You have to write these intercepts on taking A, B, C as units. So you must write only 2, 3 and 6. Now what we have seen in the second step? In second step you have seen we have to take the reciprocal of these intercepts. So the reciprocal of 2, 3 and 6 will be what? These are 1 by 2, 1 by 3 and 1 by 6. Now in third step you have seen you have to take the LCD. LCD means LCM of denominator. So I have mentioned it here. You can see LCD means LCM of 2, 3 and 6. And LCM of 2, 3 and 6 will be what? That will be equal to 6. Okay, that will be 6. Now in fourth step we simplify, and what we do, we will simply multiply all these reciprocals by this LCD. So you can see the first reciprocal is 1 by 2. After multiplying it by the LCD 6, we will get 3. The second is 1 by 3. So 1 by 3 into 6, that will be equal to 2. And third one is 1 by 6. So 1 by 6 into 6, that will be equal to 1. So these numbers obtained after this simplification, these are the Miller indices of that very plane. And we will write these three numbers inside the bracket. So Miller indices of this plane whose intercepts on the crystallographic axis are 2A, 3B and 6C. The Miller indices for this plane is 3, 2, 1. Okay, I think you have clearly understand how we can find the Miller indices of a given crystal plane if the intercepts on the three crystallographic axes are given. Okay. Now we will see some most important facts regarding the determination of these Miller indices of a crystal plane. So I have written all these facts one by one, step by step. For example, in first important fact, you should see for an intercept at infinity, the corresponding index will be 0. When you say that the crystal plane intersects the crystallographic axis at infinity, when it will take place? Actually, when the crystal plane will be just parallel to the crystallographic axis. You know, the two parallel lines does not intersect one another, and we simply then mathematically say that those two will intersect at infinity. So in this case, actually, if the plane is parallel to one of the crystal axes, then the intersection will be at infinity, and in that condition, the intercept of the plane on that crystallographic axis will be infinity. And when you will take reciprocal of this infinity, this will be 1 by infinity, and that will be 0. And if you will multiply this 0 by the LCD, even after that you will get 0. So it is obvious that for an intercept at infinity, the corresponding Miller index will be always equal to 0. There is no need to find it. Okay. I think we have understand. Now it is also possible that a crystal plane will cut or intersect the crystallographic axis in negative side of the origin, and in several cases we also shift the origin. You will see in the second part of the lecture when we will discuss the direction. Then you will say to find the direction we can shift the position of origin. Okay. So in fact in this condition the intercept may be negative if it is in left side of the origin or in downward side of the origin, then the intercept will be negative. Okay. As you can see in this figure, if this origin O will be shifted to this point, let us say O dashed, then the coordinate of this point O will be taken negative. Okay. And in that condition, a crystallographic plane will intersect the any crystallographic axis at a point whose intercept will be negative. So in this case, when the intercept is negative, in that condition, the Miller index is written by writing a sign of bar over that number. Let us see if you get the intercept, if you get the Miller index is -3, then we will not write -3, but we will write 3 over bar. So I have mentioned it here. You can see if a plane cuts an axis on the negative side of the origin, corresponding index is negative, and it is indicated by putting a bar on the corresponding number of Miller indices. For example, if you consider the 6 faces of this cubic, let us say consider that this is a cubic crystal and it has 6 faces, and the Miller index for the 6 faces of the crystal of this cubic crystal will be what? This will be 1 0 0 0 1 0 0 0 1. Okay. And when we will take the corresponding faces or the parallel faces, then the faces will be in the negative side, and in that condition for the other 3 faces of this cubic crystal, the Miller indices will be 1 bar 0 0 0 1 bar 0 and 0 0 1 bar. Okay. So these are the Miller indices for the 6 faces of a cubic crystal. Okay. And this is the technique of writing when the intercept is in negative side. I have mentioned it here, you can see. Okay. Now actually, as you can see, all the faces of this cubic crystal are identical. So all these Miller indices are identical. And this set of identical Miller indices are written by writing only the Miller index of any face, any set, but inside the braces, inside the curly bracket. So if you write Miller indices of a face of a cubic crystal like this, 1 0 0 inside this curly bracket or braces, then this will represent the set of all these Miller indices which I have mentioned it here. So you can see I have written a family of planes of a particular type is represented by enclosing the Miller indices of any one of the planes of that family into braces. Thus, this 1 0 0 inside these braces or curly bracket represents the family of planes of the faces of a cubic crystal, as you can see it here. Okay. So this is the third most important fact regarding the Miller indices. Now, when you write Miller indices of a crystal plane in this notation HKL, don't be confused that this set of three index will represent one and only one crystal plane. Actually, this set of three integers, which are called Miller indices, does not represent one and only one plane, but it represents all those planes which are parallel to that plane. So any set of Miller indices represents the set of parallel planes. For example, if you write the Miller indices of a plane like 1, 1, 1 or 2, 2, 2, -3, -3 and -3, actually these intercepts are for the same plane. Okay, so the planes whose intercepts are like 1, 1, 1, 2, 2, 2, -3, -3 and -3, all are shown by the same set of Miller indices. Okay. Now, as you can see here, 1, 1, 1, 2, 2, 2, -3, -3, -3. If these are the intercepts, then the Miller indices are same. So you can say in this notation, actually the actual value of intercepts are not very meaningful, but it is their simplest ratio which is meaningful. As you can see that the ratio of 2 is to 2 is to 2 is simply equal to 1 is to 1 is to 1. Simply the ratio of -3 is to -3 is to -3. This is also equal to 1 is to 1 is to 1. So we simply say that in this notation only the ratio of indices are important, not the actual value. So you can say, for example, that 6, 2, 2 planes and 3, 1, 1 planes, these are same planes, not different. Because when you will take the ratio of 6 to 2, you will get 3, 1, 1. Okay. So here ratio is meaningful, not the actual value. Actually, the different planes of a cubic crystal will be invariably used in further lectures. So I have shown for your convenience here three important planes of a cubic crystal. You can see the plane ABCD in this first figure, and the Miller indices for this plane ABCD will be 1, 0, 0, 1, 0, 0. And in this figure, for the plane ABFE, see the figure ABFE, the Miller indices will be 1, 1, 0. And the most common plane in a cubic crystal is AGE. As you can see this figure number 3, AGE. And for this AGE, you can see this plane intersects the three crystallographic axes at point A, G and E, and its Miller indices will be 1, 1, 1. Okay. Actually in first figure, this plane ABCD, you can see this plane is parallel to the crystallographic axis x-axis, and this is also, this is not x-axis, this is parallel to the axis y-axis and z-axis. Okay, y-axis and z-axis. So corresponding to y and z, the Miller indices are 0, 0, but it is this x-axis is perpendicular to it, and corresponding to that the Miller index is 1. Okay, but in plane ABFE, this is actually parallel to the z-axis, okay, and so its Miller indices are 1, 1, 0. Actually, I have not calculated it here. We will see later on how we can actually calculate it. But you should remember that these are the three important planes in a cubic crystal, and their Miller indices I have marked here. Okay. So this was the concept of Miller indices, how we can find the Miller index. And in the second part of this lecture, we will see how to determine the different directions in a crystal. For example, if you want to know what will be the direction of the diagonal of this cubic crystal, what will be the direction of the diagonal of a face of a cubic crystal, how we can determine. This problem will be dealt in the second part of this lecture. Okay, thank you very much.